as we've seen in modules before, it's clear that data can take different forms. Many times we'll have data sets that come from a series of data points taken at regular intervals, daily, monthly, quarterly. These types of data sets are known as time series data sets, and they're used to forecast. Generally, we want to have a set of data that will allow us to forecast future periods, such as forecasting our sales for the next 10 weeks, forecasting our sales for the next few months, or even forecasting the number of website visitors that will occur over a given set of days. Now, forecasting is very popular for prediction and learning algorithms, and we use forecasting to predict these future events. We can use it in sales, income, even predicting the number of customers that will come in future periods. In many cases, like stock prices, the future periods are based on the recent periods. And it should be obvious that this isn't totally random. If a stock price is 75 on one day, the next day it's going to be around that 75, and it will be influenced by the 75 itself. So each successive observation or each successive data point is based on the ones before it. The ones more recent in some cases may be more relevant than the ones, say, 15 weeks ago or 15 months ago. And so we may want less weight or no weight at all attributed to them. So, for example, we might want to predict sales over the next few months. We can even use the data to predict quarterly GDP, predict the number of website visitors that will occur over a set of weeks, or even predict an individual or indexed stock. And we're going to use the historical information to predict these future data points. But you have to remember that there's no guarantee that the future performance will behave exactly like past performance. So what we're doing is we're trying to hope that this will get as close as possible, and then identify other attributes that can affect our predictions. Now, you might ask, why can't we just use regression like we had before? Well, technically, we will be using regression a little bit later for some time series problems. But consider the graph that we have here. And it shows the closing data for NASDAQ in March 2018. Now, it should be clear that each data point is some way related to the previous data points. Remember that in regression, one of the assumptions is that the errors are independent, meaning that the error of one day is not related to the error in another day. If we run regression on a time series set of data, we will certainly violate this assumption. And we might violate other assumptions as well, but this is the most common. So regression is going to give us a problem if we just use it by itself. And we'll talk about this a little bit later. Now, there's two types of models that we will discuss: an extrapolation model and an econometric model. Extrapolation models will use the historical data for predictions and examine the previous data patterns and therefore extrapolate or extend the application of future information. So if we see a line that's going straight up for about 5 or 6 periods, we're going to assume that the next n number of periods it will go up by the same amount. It's very simple to understand and very simple to interpret. The challenge, however, is how well will that work over a longer period of time? Ideally, we would hope that our predictions will work for as long a period of time as possible. Now, econometric models are called causal models because they will use regression to forecast time series data. And it's very powerful, very complex, and very useful in explaining intricate relationships between the variables. And in this case, we have methods to deal when we have violations of assumptions. So under extrapolation models, consider we have this chart, this basic chart here. One could easily estimate future predictions as a straight line from point 15 onward. It's basic, observational, but it is an extrapolation technique. There are many different ways that we can do this. We can do this what's called trend-based, where we use regression to estimate just the trend component. Autoregression, where we use previous periods as a weighted factor of future performance. Moving average, which is a concept of using periodic averages, such as a 2-period, 3-period, 7, 21-day period moving average. And exponential smoothing for nonlinear trends and curved growth. In econometric models, which are widely used in finance and economics, we use regression techniques and include a variety of terms to help with the violation of assumptions, such as lag effects, moving average effects, difference effects, which are the difference between period t and t-1, additive effects, which are additional variables not respective to time, which is where we get the added enhanced power of explanation to understand what is causing changes in the model. And we can use these models not only to provide the prediction, but to control for the effects of time, allowing us to understand the effects of those added variables. So looking at trends are fairly intuitive. If we look at a graph, we can clearly see when a trend increases or decreases. Some of the other curves we can see them clearly, but they're not as necessarily easy to interpret. So take an exponential trend where it begins to curve. So this is a curved linear relationship. And then we have a different type of curve where we actually have two curves. We see here where we create this well-known S curve. We also have the concept of seasonality. So seasonality means there's some periodic or cyclical pattern to the data. And we can differentiate seasonality as occurring between a year. However, the same concept is whether it occurs intra-year. We can have a seasonality or a periodic change within a quarter. The right side shows a graph containing a seasonality component. The length of the cycle can vary and is determined by your various business activity. In the top case here, we have a seasonality with a trend where we have the linear trend going up and a seasonality effect that occurs every fourth period. In the bottom graph, we have seasonality without trend, where we just have our peaks and valleys that seem to occur, and there's no linear trend associated with the graph. Another critical component, which we'll also talk about more in the next module, is randomness. Randomness is a key component of time series data, and it represents the uniqueness of the data, or the noise, or sometimes known as white noise, beyond the elements of the trends and seasonality. Once we account for the trend and seasonality, we can measure all variables against this randomness to see if they can predict the random variation, just as we would do in regression. So let's understand this. If we have the graph on the left here with the trend with randomness, we know that there's a trend component, and if we run a regression equation, we will end up in a situation where we will violate the assumption of independence of residuals. If we are able to remove the trend component, we're left with a graph here on the right. And what will then happen is we now know that there's no effect for time. So therefore, the movement or the variance left in this graph or in this data can be attributed to other variables. And we can perform our regression equation, as we had done before, to figure out what the effect of those variables are on this detrended graph, or what we are called the random noise graph. Now, how do we measure accuracy? Well, the most obvious way we can measure accuracy of forecasting should be, well, how well does it predict? And how well it predicts is a measure of the error. So what we're going to ultimately do is we're going to look at the prediction and subtract it from the actuals, and from there determine how well it's doing. Now, the problem you have is when we just take the error, we're going to have a lot of positives and negatives. So you may be off by 300, you may be off in the next period by negative 200, and so forth. And so the scope of which will tell you how high and low you're going to be. While that's one measure of accuracy, that may not be the best one. So the next way to do would be let's just take the mean absolute error. Let's take the absolute value. So we're getting rid of the negatives. So we're really understanding how far away from the mean this actually is. So we're understanding how far away from zero our errors actually are. And that's what the mean absolute error is. It's the measure of the absolute value of the error and taking the average. Now, another way to do this is to take the square root of the sum of the squares of the errors. So we take the errors and we square them. And again, what that does is, if you remember from previous modules, that gets rid of the negative, but it also expands and creates that added spread for errors that would be further away from the center or further away from zero. We divide that to take the average, and then we take the square root, and this gives us a measure. Now, what we can also do is take the mean absolute percentage error. So instead of just reporting on error, we're going to report on the percentage error. So we can end up with a number that says our mean absolute percentage error is about 4%. And if that's the case, then we're saying that our roughly percentage error that we get will be around plus or minus 4%. So measuring accuracy in terms of the errors is really up to the analyst to determine which ones are better or not for the particular analysis that they're doing. But it's a good practice to calculate all of the error measures so that you have a very good indication of how your model is performing.